Hello, my dear students. Good morning. Hope you all fine. See, take care about your families and you also concentrate more on studies and don't think about anything. So, in this particular time, we cannot do anything more than this. So, maximum we have to work hard. See, we are ready to help you in any manner. If you have a doubt in a particular topic and don't feel hesitate, please ask me or ask any particular faculty. We are ready to explain. Okay, so this is a very important, this especially this S block. Of course, I agree one thing, this is completely theory part, bit boring, but we will have 15 questions from inorganic chemistry, so like S block. Okay, next hydrogen and its compounds I will start maybe next class, and P block elements. Okay, coordination compounds in second PUC, D and F block. These are just inorganic chemistry, and periodic table we know already, chemical bonding, inorganic chemistry. So already 5 questions over from inorganic chemistry. So remaining around 7 questions, we will have 7 to 8 questions in second year inorganic chemistry. Maximum around 9 questions also can possible. Okay, so now we will have S block and you have to listen carefully. Okay, let's start about chemical properties of alkali metals actually. So first one, alkali metals means everybody knows lithium, sodium, potassium, rubidium, cesium, okay, francium. Of course, francium is radioactive. So first one is alkali metals reaction with hydrogen. Reaction with what, sir? Hydrogen. Alkali metals when react with hydrogen, what you will have? Hydrides you will have. What you will have? Hydrides. Hydrides means what? H minus. Because alkali metals are less electronegative than hydrogen. So their electronegativity values you know already. So hydrogen is more electronegative. Certainly hydrogen has minus charge in hydrides. Okay, simply they form MH. What they forms? MH like this. So alkali metals when react with hydrogen, they forms hydrides with the formula MH, M plus and H minus. So alkali metals like anything else like lithium, sodium, potassium, rubidium, okay, cesium and all, on heating you will get MH. Actually this is the formula, MH, hydride. Lithium hydride, how to have? Lithium when react with the hydrogen on heating up to 1073, high heating is required. Okay, both are small. Actually as going down the reactivity increases, you know that, because as going down size increases. So lithium is somewhat less reactive, then you will get what? LiH. LiH, lithium hydride, Li plus and H minus. 1073 Kelvin is required. But remaining all M plus H2, you can have just 673 Kelvin. At 673 Kelvin, you will get MH here. So what is M here? M is sodium, potassium, rubidium and cesium around this temperature. And as you are going from sodium to cesium, this temperature can decrease. So what is the order of reactivity? Order of reactivity, if you see, lithium is less than, sodium is less than, potassium is less than, rubidium is less than cesium. So they are forming hydrides in this particular MH formula, and this is the order of reactivity. That means who can react fast? Cesium can react fast. Okay, and as going from lithium hydride to cesium hydride, LiH, NaH, okay, next KH, next what we got, RBH, rubidium hydride and cesium hydride. If you see, as going from lithium hydride to that CSH, ionic nature increases. Ionic nature increases. Why? You know electronegativity values. Lithium, what is electronegativity? Lithium, I will write here. Lithium electronegativity is 1 and hydrogen is 2.1. 2.1 hydrogen. And cesium and hydrogen, as going down electronegativity decrease. So electronegativity difference increase or not? Tell me sir, as going down that electronegativity decreases. Cesium actually 0.1 we have to decrease. I said lithium is 1 and sodium is 0.9, 0.9 and potassium is 0.8, rubidium is 0.7, like this I given, and Mr. Cesium is 0.6. So 0.6 to 2.1. Electronegativity difference is more. So why I am telling you? To avoid confusion and to avoid some what kind of remembering. Okay. So we have no need to buy it. To avoid by hacking, I am telling all these things. So easily you can remember. Electronegativity difference is more. So cesium hydride is more ionic. Cesium hydride is more ionic. So lithium hydride, you will have what character? Covalent character. What character? Covalent character. So lithium hydride, you can answer, you can give answer in another way also. Why lithium hydride is having covalent character? Li plus, it's a small, hydrogen small. However, hydrogen is common. You have to compare only size of metal ion. Here Li plus small, Cs plus big, hydrogen small. So between these two there is no sharing nature. Like that also you can answer. What I am saying, understanding? As lithium is small, as going down size increases, either atomic radius or ionic radius. As going from lithium to cesium, size increases. So cation size is big, anion size is small. Certainly they won't have a sharing nature in cesium hydride. Like that also you can say. So I have one more question. In polar solvents, who will dissolve more? Cesium hydride dissolve more because ionic means polar. Ionic means what? Polar. Polar dissolve in polar. Like dissolve like. So among these, who can dissolve in water easily? Like that they will ask you. Who dissolve in polar solvents easily means cesium hydride. Otherwise they will ask order of solubility in water, means you have to follow this order. Otherwise, what is the solubility order in non-polar solvents like benzene, CS2, carbon disulfide, CS2, CCl4, then LiH. Non-polar means because covalent are non-polar, ionic is more polar. Understand? So these are less soluble in water, but these are more soluble. You can write. You have to write. Okay? So this is the order of ionic character, and this is also order of solubility in this way. Okay, ionic character, and as going down solubility, going down lithium to cesium, solubility increases in what? In water. In water solubility increases. This is very important. So why this is ionic, I said. Got it everyone? And these hydrides have high melting and boiling points because they are very closely packed. Okay, so lithium hydride having covalent character. This is about hydrides. Okay, so reaction with hydrogen gives hydride. What is this? Hydride. Lithium hydride or sodium hydride, potassium hydride, like that. Okay, so this is reaction with H2. Next one is reaction with air. Reaction with what? Air. Air means actually O2 and N2. So N2 is inert, but because of a small size, lithium can combine with N2 directly. Remaining all won't. Okay. So this is very important. So about hydrogen reaction, you have to write, sir, first. Hydride formation you have to write. Okay. Next, we will discuss about reaction with air. So lithium, when react with O2, it forms only Li2O, lithium oxide. What is this? This is oxide. because of its small size, lithium cannot form peroxide and superoxide. So alkali metals or alkaline earth metals, when react with oxygen, there are three types of oxides are possible, as we discussed in redox reactions: oxide, peroxide, superoxide. So lithium forms only oxide, remember, because of its small size. As size increases, cation size, here alkali metal ion will be there, no? Lithium Li plus, sodium Na plus, so like that Cs plus as going down. As cation size increases, then superoxide stability increases. Remember this one. So here I given very clear point. Lithium, when combined with oxygen, forms only what? Oxide. It forms only oxide. That's it. Okay. So lithium cannot form peroxide and superoxide. I have no need to write that point because it forms only oxide, I said. Oxide means everybody have idea. Oxide means oxygen charge is -2. Okay, like that. And come to next, sodium. Sodium, when react with O2, when this is limited. What is the meaning of limited? Less quantity of O2 when react, then you will get oxide. Oxide means what? Na2O you are having, oxide. Sodium oxide. So here charge is O -2. Limited oxygen. But if they said like this, sodium burns, okay, burns in oxygen, means excess. What is the meaning of this? Burning means more oxygen. Okay, sodium burns in oxygen, then peroxide. What is the product? Peroxide. So sodium, when react with O2, then you will get Na2O2. What is this? This O2 excess or lesser? Excess. This is excess of O2. When react with sodium, you are getting sodium peroxide. What is this? Sodium peroxide you are having. Peroxide means everybody knows O2 -2. How we are saying? 2 Na plus, so O2 -2. I repeat, 2 Na plus and O2. Okay, 2 Na plus and O2 -2. But here 2 Na plus and O -2, only one oxygen, O -2. But here two oxygens, O2 -2, like this. So sodium will give both oxide and peroxide, but lithium, when react with O2, that gives only oxide. This is a very important point. So you have to write all these things. Okay, sir? So have a screenshot and write it. And one more important thing, that remaining are there: potassium, rubidium, cesium. They form oxide, peroxide and superoxide also. Depends on the quantity of oxygen. As quantity of oxygen increases, then you will get superoxides. Okay, superoxides are more stable as the size of cation increases. This is very important because they'll ask you which superoxide, even peroxide also same story. As cation size increases, peroxide stability increases. Even superoxide, as cation size increases, superoxide stability increases. So these are important. Please have a note. And now I will give you about superoxides. Okay. So as I said, when potassium, rubidium, cesium, when react with oxygen in excess, so all three possible. So M I will write M plus O2. Okay. It gives M2O. M2O. What is M here? M is potassium, rubidium and cesium only. Okay. So very important. Listen carefully, sir, please. Okay, and now this, when O2 is limited, as I said, limited, as quantity of oxygen increases, This also possible. M plus O2. So optimum oxygen means what required. Okay, then you will get M2O2. M means what? Potassium, rubidium, cesium. But lithium, why I am not including here? Because lithium forms only oxide. Sodium separately written. Sodium gives both oxide and peroxide. And now this M plus O2 you will get when oxygen is a more excess as I said, excess enough, excess, then you will get MO2. What is M here? I repeat, potassium, rubidium, cesium. So this is actually oxide and this is peroxide and this is superoxide, like this. So about stability, if you see stability of peroxides and superoxides, if you see peroxide stability, if you see, that will be starts from sodium, while lithium cannot form peroxide. Na2O2, even oxide stability also same. As going down increases. Simple, as going down reactivity increases. Lithium to cesium, who is more reactive? Cesium. Okay. So stable products you will have as going down. Na2O is, peroxide, no? Na2O2, K2O2, Rb2O2, CS2O2, like this. This is peroxide stability. Let's see superoxide stability. Superoxide stability. As going down, what happens? Same story. Superoxide stability. So I said very clearly, as cation size increases, it can be applicable for second year group elements also. As cation size increases, then stability of peroxide and superoxide increases. This is very, very important. As cation size increases, then stability increases. As I said, KO2 only I can write. Why KO2 understood? O2 minus. So peroxide and superoxide means what is oxygen charge? I forgot to write here. O2 minus. Okay, so KO2 is less than RbO2 is less than CSO2. So superoxide stability also as going down increases. So this is a very, very important. Please write down all these things. So this you written maybe already. So one more thing, superoxides, in that what is oxide structure and what is the nature of superoxide we have to see. Oxides are O2 minus 2. Okay, peroxides, oxide O minus 2. So that is diamagnetic oxide. Okay, and O2 minus 2 diamagnetic, but O2 minus, it's a paramagnetic because having unpaired electron. So we have to discuss about this nature of oxides now. Nature of oxides. If you see oxides, O minus 2, right? Oxygen valence electrons how many? 6. Minus 2 means 2 electrons taken. 6 plus 2, 8 electrons. So even number of electrons. So there is no unpaired electron. So this is paramagnetic or diamagnetic. The concept you have in MO theory, chemical bonding. Paramagnetic, diamagnetic. Paramagnetic means attracting towards magnetic field due to unpaired electrons. Dia means that won't attract towards magnetic field. Diamagnetic substances have completely paired electrons. Okay. Next is peroxide. Peroxide means O2 minus 2. Everybody knows. So how many valence electrons? 2 oxygens. So 2 into 6 plus 2. So total 14 electrons. O2, 2 oxygens. Sir, oxygen 8, no sir. 8 is atomic number. Valence electrons I am writing. What I mean, because valence electrons only involved in bonding, you know. Lewis dot structure, everything, you know, already. So valence electrons I am writing. Oxygen is 6th group, so 2 into 6 plus 2, 14 electrons. Now, what I am writing, understanding? Valence electrons. Next, superoxide. Superoxide means what? O2 minus. So, in superoxides, what valence electrons you are having? Means O2 minus means 2 into 6. 2 into 6 plus 1. Minus 1 means it gained 1 electron. So, plus 1. So, ulta. Correct now? Positive charge means lost electron. Negative charge means gain electron. So, total how many electrons are there? 13 electrons. 13 electrons means even or odd? Odd. That means who is paramagnetic? Superoxide is paramagnetic in nature. Come to this, oxide and peroxide are diamagnetic. Please have a look. This is very, very important. O minus 2, 2 is the minus 2 is the charge, minus 2 is the charge. 2 electrons gained, so 6 plus 2. So 14 electrons, 7 pairs, O2 minus 2. If you see peroxide and superoxide, O and O. Okay, so total 14 electrons. So I will write minus 2 here. So this is peroxide structure. Now 2 electrons I written here. Otherwise I will write 1 pair here. 14 electron means 7 pairs or not? So here you have 1, 2, 3. 1, 2 and 3. This is O2 minus 2. This is structure, what it is? Peroxide or superoxide? This is peroxide structure. Superoxide, this is peroxide structure. Superoxide structure, same O and minus 1 only. So now this time you have 1 pair here. So 13 electron means 6 pairs and 1 unpaired electron. Correct? 13 electrons. So 1, 2 and 3. Total 1, 2, 3, 4 electrons, 6 pairs. So 1 and 2. Sir, 2 pairs here, 3 pairs here possible? Yes, you can write, not a problem. So you can write like this, 1 unpaired electron. Okay? You can represent like this. This is what? This is the superoxide structure. Superoxide has 1 unpaired electron or not? See this? 1 unpaired electron you have or not there? So don't take this is 1 more electron. Okay? So it have 1 unpaired electron. So superoxide is what magnetic character is having? Paramagnetic. They'll ask you which of the following is a paramagnetic or which of the following have unpaired electron. Like that they can ask. Okay? Very, very important. So this is about superoxide and peroxide. Okay? This unpaired electron you can write here and pair you can write there. Those we call as resonating structures. Understanding? That is also correct. I repeat, this unpaired electron here and that pair there. You can write. It's not a problem. Okay? So this is about what? Oxides. Okay? As going down, stability, how changes, that also I am writing every time. Okay, sir? So I will arise. So before that, please have a screenshot. Okay, sir? Or pause the video and write down. So please, as I am telling you many times, you have to focus more and you have to listen every class, and best we have to see. You can say in future, and during pandemic condition I became a doctor, I became a great engineer by watching online classes only. You can say like that also. Okay, so please take care and practice more. Okay, don't show any negligence, please, my request. Next is reaction with halogen. Reaction with what, sir? Halogen. Halogen means what? Fluorine, chlorine, X you can write, bromine, iodine. With this, how the reactions happen, let's see. Okay, so with the alkali metal, With whom? Alkali metal. M iodide. M means like lithium, sodium, and potassium, rubidium, cesium. These. Francium, why I am not writing understanding? That is radioactive. So now what you will have? Very simple. These two will react. How you will have? From many ways. You have oxide like M2O when react with HCl. You are having 2 moles like this, and you are having even HX you can take. Simply commonly. X means fluorine, chlorine, bromine, iodine. Then you will get 2MX plus H2O. Like this. Not only this, preparation of halide, not only this. You know, sodium hydroxide, neutralization reactions. MOH when react with like HX. What you will get? MCl. MCl plus H2O. Like this. Okay, not even that. Carbonates. M2CO3 when react with some HX. You will get 2 moles. What you will have here? 2MCl why I written? Sorry, X. 2MX and H2O plus CO2. These are the preparations. Okay, so you can have few more important points, their stabilities and all here also. Okay, for given similar halogen, what happens? Ionic nature increases. I repeat, if the halogen is similar, means here you have suppose LiX, okay, LiX, and here NaX, Kx, Rbx, CsX. So for given halogen, okay, halogen is same but alkali metal will be different. Okay, for those as going from lithium halide to CS halide, ionic character increases. Same story, any halogen you can consider. The cesium electronegativity is less, so electronegativity difference will be more. Certainly this will become ionic. As I mentioned in previous, no worry. Electronegativity values, if you know properly, you can say. So CSX is ionic, more ionic. So LiX is having covalent character. Like this. So that's why lithium halides are less soluble in water. Less soluble. Lithium fluoride, lithium chloride, whatever. Least soluble in water. This soluble in water more. As I said, ionic compounds are more soluble in water. So no confusion. So who is more soluble means cesium halides are more soluble in water. Lithium halides mostly they are less soluble in water. Okay. So here like that. It's very, very important. Okay. And one more, with same halogen. With the same halogen. Same halogen written already. With same alkali metal. Now here ionic nature increase, their covalent nature increase. So I repeat, for similar halogen, ionic nature increase, different alkali metal. Here X can be anything like fluorine, like that. X can be similar. This X can be particular one, either fluorine, either chlorine, either bromine, either iodine, like this. Understanding? Suppose I will write like this LiF, okay, NaF, okay, next Kf, next Rbf, next cesium fluoride. See, for similar halogen, fluorine. Instead of fluorine, you can consider chlorine, whatever. As I said, as going from lithium halide to cesium halide, ionic nature increases. Already I given symbol, so ionic nature increases. So this is the order of ionic nature. So lithium fluoride is having some covalent character and highly stable because both are small. Lithium is small, fluorine is small because halogen, you know now. So that's why it is. Actually, it is ionic. More cesium plus is big size, fluorine is small. So this one is more ionic actually. Okay. So now this for given similar halogen and same similar halogen and different alkali metal, you have like this ionic character. Our next thing is for given similar alkali metal now. For given similar alkali metal, what happens? Now I'll take similar alkali metal now. That means M, F, M, Cl, M, because alkali metal is similar now. M, Br and M, I. Very, very important. You will have questions. Which is more stable? Which is more ionic? Which is soluble in water? So I am not writing who is soluble in water. You have to write ionic substances soluble in water easily. Okay. So now what happened here? Ionic character decreases. That means this MF is a more ionic and this MI is having covalent nature. Because see, electronegativity value is important. From that you can say easily. Only trick, otherwise you will get confused. Pakka. See, fluorine more electronegative. So difference is more. Because alkali metal is same everywhere. So here iodine is less electronegative. So difference is less. Electronegative difference is less. So covalent. That's it. Understanding? So in water, if I take something like with cesium fluoride, cesium chloride, cesium bromide and cesium iodide. Who is more ionic means this is more ionic and this one is more covalent. So this one is less, this one less soluble in water. Very simple. Less soluble in water. That's it. Understanding? So this is ionic, that is covalent. So ionic nature, what happened here? Ulta. Here ionic nature increased from lithium to cesium. But here the same alkali metal, different halogen. Ionic nature decreased. So ionic nature here increased, but here ionic nature decrease. Reason? No need to confuse. Reason? Electronegativity differences enough. That's why in periodic table itself I was given one shortcut. Few people are forgetting all those things what we done in offline classes. We discussed many times, we revised periodic table, everything. So sad. So fluoride, chloride, bromide, iodide, like that. So here ionic and covalent. So ionic nature what happened? Decreases. So now my question, why cesium iodide is less soluble in water? Because both are big size, you can say, one reason. Another reason you can say, electronegativity difference is less, that's why covalent nature is more. Covalent means non-polar. Non-polar means they cannot soluble in water because water is polar. Non-polar cannot soluble in polar solvent because water is polar or not? Water is polar. This one is very, very important. Okay, sir? So these are about some halogens. I will give few more stabilities also later on at one particular place. Okay, so please have a look all these things. Okay, write down these also please. Okay, sir. Thank you. Now we will have one more important with the lithium halogens. Lithium halogens are lithium halides. We cannot say halogens. Lithium halides. Lithium LiX mostly is soluble in non-polar solvents. What solvents? Non-polar solvents. Non-polar solvents like alcohols, CCl4, CS2, like that. They can be soluble. One more I will give you here. Lithium fluoride. Okay, with fluorine. Lithium fluoride and with fluorine. Lithium fluoride, sodium fluoride and KF and RBF and CSF. Who is more stable if you see? So here, if you see fluorides, so lithium fluoride is a more stable. Thermal stability. Okay, this one important. If I take LiI, MAI and KI, RBI and CSI, if you take, this is the order of stability. Why, sir? What's the reason? Simple, common sense. Lithium is a small, fluorine is small, so stability. But here, lithium is small, but iodine is big. So this definitely have less stability. So this is less stable like this. Okay. So till here, what we discussed, you please try to remember, and few more last or almost few stabilities I will give you, and otherwise I will write on paper and I will send in our WhatsApp group, that also I will do, and few anomalous behaviors and diagonal relationships, those also I will send, and I will revise for 5 minutes like that, and I will enter into alkaline earth metals. Alkaline earth metals 1 day or 2 days, that's it. Okay. And hydrogen and its compounds, very small chapter, only 2 concepts, one is deuterium and one is hydrogen peroxide, that's it, 2 classes. In 4 classes, inorganic chemistry will complete. Only P block is there. Actually, in P block, 13th and 14th here we have. But 15, 16, 17, 18, those groups we have in second year. So, all groups at one place we will discuss, because all groups from those you will get 7 to 8 questions. Believe me. So, that much important. At one place we will discuss. So, our syllabus almost completed. You have no need to worry. Just hide this S block, alkali metals over, just alkaline earth metals. 1 day is enough. 1 day or 2 days. Hydrogen and its compounds, 3 days. Total 5 days. 2 days or 3 days enough. Slowly I am giving every point. So you have to understand what we are doing. Please. Okay. Thank you very much. And one more time telling you, please take care. Okay. And all the best. You have to prepare.